Okay, so let's get into some samples here. First off, let's say we have 28 mils of nitric acid. We add it to 53 mils of 0.320 molar potassium hydroxide. We want to know the grams of water. Okay, we also want to know concentration. Remember, concentration is molarity, which is moles per liter, of hydrogen and hydroxide after the reaction is complete. So this is kind of what we were talking about with the leftover ion concentration. Okay, so how are we going to do this? Well, first off, like always, let's talk about a balanced chemical reaction. You have nitric acid plus potassium hydroxide. That's going to give us water. I'm going to write it as HOH, and potassium nitrate. Now, from the get-go, we know that the nitrate and the potassium are spectators. Okay, so our net ionic reaction here is going to be hydrogen ion plus hydroxide gives us water. It's a nice one-to-one, which makes all the math much easier. Okay, now what did they give us? Well, they gave me volumes and they gave me molarity. So step one is going to be, first off, to figure out the moles of all of the solutions, so that I can then figure out my limiter and then predict how much water. So for the nitric acid, I've got 28.0 mils. Now I know I told you don't have to show me this step, but in 1 liter there are 1,000 milliliters. Okay, so that's going to get us to liters. Then we need to multiply by the molarity. So we've got 0.250 molar nitric acid in 1 liter. So that's going to allow us to figure out that we have 7.00. Now let me get rid of that because it'll be confusing here. Okay, 7.00 times 10 to the negative third moles of nitric acid. Now, I think it's also important to point out that we also have 7.00 times 10 to the negative third moles of hydrogen ion. Why? Well, because there's only one hydrogen ion per mole of this substance. If this was a 2 for sulfuric or a 3 for phosphoric, there's one of the curveballs, but we start off with the ones-to-ones while we get the process down. Now, for potassium hydroxide, you've got 53.0 milliliters of potassium hydroxide. All right. We're going to have, again, 1 liter, 1,000 milliliters. And then multiply by the molarity, so by 0.320 moles. I'm going to run out of space here, so I'm going to cram this up here. Potassium hydroxide in 1 liter. So that gives us 1.700 times 10 to the negative second moles of potassium hydroxide, or hydroxide itself, because there's only 1 mole. So now when I look at both of these, it's a 1-to-1 ratio. So what I don't have to do is then do a step of, I could, but to then show how I know which my limiter is. If you were doing the chart, remember, and it's not a 1-to-1 ratio, this is where you then would come back up here and do your moles, your change in your X to determine what your limiting reactant is. Or for those of you doing dimensional analysis, you would do another step for the mole ratio. Since this is a 1-to-1, we can simply recognize the fact that my nitric acid is going to be my limiting reactant because I have the smallest number of moles of that. Okay, so now the next thing that I can do is I have to, again, what am I trying to solve for? I'm trying to figure out the grams of water, and I'm trying to figure out the concentration of hydrogen and hydroxide when I am done. Okay, grams of water should be pretty easy because we have our limiting reactant, 7.00 times 10 to the negative third moles of nitric. And as we saw in our balanced chemical reaction from the last slide, there was 1 mole of water for every 1 mole of nitric. Done. So I get 7.0 times 10 to the negative 3 moles. Actually, it didn't say grams of water. It did want to know grams of water. I'm lying. Okay, grams of water. So there's my moles. I'm going to squeeze this in on the end so I don't waste another space here. But then we multiply by 18.02 grams of water, or molar mass. Okay, we end up with 0.126 grams of water. Okay, relatively straightforward. Now, in order to figure out your concentrations, I want to just show you a little picture here. All right, in theory, our hydrogen ion was our limiting reactant. What they're trying to figure out is how much is left. So since hydrogen was the limiting reactant, there is none left. There should, in theory, be absolutely none left. So my concentration of hydrogen ion is simply going to be 0 for the molarity. It was my limiting reactant. Anytime you can determine something is your limiter, there's not going to be any left. Now, for the hydroxide, this becomes an excess reactant problem, which still comes back to the fact of what I had available, subtract what you used, and then you have what's left over. We're not quite done because it's molarity, but so what do we have available? Well, last slide we found 1.700 times 10 to the negative second moles. What I used is a 1-to-1 ratio, so it would be exactly what I used, or what my nitric was, because everything was used up. 7.00 times 10 to the negative 3. If you'd like to use the chart, you would have taken moles. Well, it's all a 1-to-1. We would have brought it over. It wouldn't have been exactly the same. So that leaves me with 1.00 times 10 to the negative second moles of hydroxide left over. But I'm not quite done. Remember, in order to find the concentration, it's moles per liter. Well, my new liter down here is how, when I added the two substances together, in order to figure out what the new total volume was. So if you look at the very original amount, okay, you had 28 mils. I'm going to do this out to the side here. You added 28 milliliters of the nitric. You also added 53 milliliters of the potassium hydroxide. So you got 81.0 milliliters, which you need to do moles divided by liters. So it's going to be 8.10 times 10 to the negative second liters, which gives me a new molarity of 0.123 molar hydroxide. This extra ion thing is always something that trips people up, but that's how you figure out the concentration of hydroxide ions on the other end. Okay? Alright, I'm going to do another video for, pause here and do a second video for the second example.